everyone, and this is ECE23 performance task number 10, which is the Plesiochronous Digital Hierarchy, or the PDH, under the time division multiplexing. And in this topic, I will show you the examples and the illustrations of Plesiochronous Digital Hierarchy, and we will also discuss the frame format and structure of the PDH. And this is Dina C. Dagum from BSECE 3C. First, what is Plesiochronous Digital Hierarchy, or PDH? PDH is a method of transporting massive amounts of data over digital transport equipment such as fiber optic and microwave radio technologies in telecommunications networks. The word plesiochronous comes from the Greek words plesios, which means near, and chronos, which means time, and refers to the fact that PDH networks are nearly but not quite fully synchronized. Let's have the examples. Here in this diagram, we have the DS1 frame in T1 and E1. We have T1, we have the channel number 1, channel number 2 until channel number 24. The range here from channel number 1 to channel number 24 have the 125 mu s, and per the bits in each channel was 8 bits, and the total bits from channel number 1 to channel number 24 have the 193 bits. The data rate here is equals to 24 times 8 plus 1 bit divided by 125 mu s, that is equals to the 1.54 megabits per second. Here in E1, we have 125 mu s, the 0, 1, 2, 16, and until 31. The 0 here is to be called the frame synchronizations, and the middle here is the 16, which it is 256 bits. It is called the signaling channel. The data rate here in E1 carrier is equals to 32 times 8 divided by 125 US is equals to 2.048 megabits per second. Here we have the T carrier in North America. The T here this is the hierarchy for North American standard, which is based on T1. T1 max multiplexes 24, and we got the output of 1.54 megabits per second. Then we have the we need to multiplex it by 4 to get the T2 max output, which is the DS2 is equals to 6.312 megabits per seconds. Then the next level here is the T3 max, which we multiplex it by 7 to get the output of DS3 equals to 44.376 megabits per seconds. The next level here is the T4 max, which we multiplex it by 6, and we get the output of DS4 274.176 megabits per seconds. As you notice, we multiply the 1.54 megabits per seconds by 4, and we didn't get the exact output here in T2 max because we have the so-called justification stuffing bits. What is the justification stuffing bits? All these two devices work in different clock devices with some variations, like may be variation of the parts per million, even with that variation over the distance over time. These data reach the input the rate varies, so they come at different intervals of time. But the thing is, when the mocks expect some data, they may not be data. So what it does is it inserts some justification bits to compensate the the speed, and it ensures the output of it is fixed. So this continues overhead and gets added at all stages. One thing that this bit interlude multiplexing, it means that this must takes one bit at a time at each and every channel to get the output. When the data rate increases, the efficiency of these muxes decreases because they got to handle in bit by bit, and the data rate keep increasing. But one of the smallest advantages of material in interleaved, the buffer and the memory, uh, of the material interleaved multiplexing is it interludes bit by bit by by the buffer, and the memory which is required for the particular muxes can be small because of need to process only small data at a given point of time. So this the hierarchy of the T carrier. Next is the PDH hierarchy, or the E carrier in Europe. The we have the PCM here, 13 mux, or the D1 level, which is the 32 multiplied by 64 kilohertz. We got that 2.048 megabits per seconds. Then the capacity of it is 30 base channels. Next level is the D2 level, which is 4 multiplied to 2.048 plus stuffing bits is equals to 8.448 megabits per second. And it has the capacity of 120 base channels. The, the next level is the D3 level, which is 4 multiplied by 8.448 plus stuffing bits. It equals to 34.36 megabits per second. The capacity of it is 480 base channels. The next level is the D4 level, which is 4 multiplied by 34.36 plus stuffing bits equals to 139.264 megabits per second. It has the capacity of 1920 base channels. The next level is the last level, which is the D5 level. 4 multiplied by 139 plus stuffing bits, it equals to 565 megabits per second. It has the capacity of 7,680 base channels. The data increases as the overhead percentage also increases. As the stuffing bits increases, and this the major drawbacks in PDH in E carrier. Next, we have the PDH hierarchy, or the interoperability. Since we have the E carrier here, we have the T carrier and the J carrier, which corresponds to the Europe, Japan, and North America. First, to convert the 64 bits, we multiplex it by 30. Then the next consecutive levels is multiplex it by 4. To convert it into T carrier, the E carrier must multiplex it the level 4 here in the E carrier must multiplex by 3 to convert into T carrier the third level of T carrier to have an output of DS3. Then also to convert the E level 1 here in E carrier, to convert it into the desired output of DS2 of T2, we will multiplex it by 3. Also, in to convert the level 2 here in T carrier to get the desired output in J carrier, we must multiplex it by 6. And that's how the PDH hierarchy interoperability works. Next is the frame format or the structure. In this topic, I will show you what is the consist of this table or the frame structure, its details and the agenda. First, we have the agenda. The agenda here is we have the alignment bits here, corresponds to the number 1 with the blue and the red digits. The letter A here with violet color is the remote alarm indicator. And the letter E with the orange color is the CRC for error signaling bits. And the green here is the with letter C is CRC4 bits. Another thing is the channel CAS bits is correspond to the blue with the letters in the box. Then we have the channel bytes, or we have the yellow with the spark uh, symbol. And the last is the letter S with the yellow color. It is called the spare bits. With this, we have the E1 carrier frame structure details, time slot 0. The time slot 0 is for synchronization and transmission management. The first bit here in TS0, we you can see here the what do you call this is the FAS frame, or the frame alignment signal, or the FAS frame. And it is used for the international use. If not used, it should be set to 1. The bit number 2 here to 8 in the time slot 0 is used for frame alignment signal. A fixed FAS 0011 or 011 is transmitted, which enables the frame alignment of each frame between transmitter and receiver. This is transmitted in the alternative frames. This enables receiver to synchronize with transmitter. The first bit, the first bit in time slot 0 is the what you call the not frame alignment signal. It is used for the international use, and by default the value should be 1. The second bit here in time slot 0, which is the NFAS also, is fixed at 1 to assist in avoiding simulation of the frame alignment signals. Can you imagine what would happen if these values become 0 and the rest of the bits sequence between B3 and B8 becomes equivalent to FAS frames pattern of 0011 or 001? The third bit here is what you call the A bit in time slot 0 and FAES. It is used for remote alarm indication. If alarm, it is set to 1, else 0. Next here is the bits slot 4 to slot 8. or the S4 to S8, and time slot 0. It is our spare bits for national use. Could be used for point-to-point applications, synchronization, status messaging. If not used, then must be set to 1. Next is the E1 carrier frame structure details time slot 0 with CRC 4. Here, where there is a need to provide additional protection against simulation of the frame alignment signal, and or where there is a need for enhanced error monitoring capability, then bit 1 should be used for a cyclic redundancy check for or CRC4 procedure. The CRC4 multi-frame composes of 16 frames numbered from 0 to 15. Each multi-frame is divided into SMF with 8 frames in each. CRC4 block size is 32 by 8 by 8, which is equals to 2048 bits or 2.048 bits, kilobits. Bit 1 in frequency alignment, uh, frame alignment signal frame would be used to transmit CRC4 bits. There are 4 CRC4 bits, which is C1, C2, C3, and C4. Frames not containing frame alignment signal are used to transmit CRC multi-frame alignment signal, which is the 001011, and error instead of 0011, and error indication bits E when CRC4 is configured. Next is the E1 carrier frame structure details in time slot 16. It is used for signaling of information between transmitter and receiver channels. During the course of the call, origination pH number, destination pH number, engage, unhook, and for intended connection signaling between caller and called party. Bit 1 to bit 4 in TS16 have fixed value of 0000, which is used as MFAS, or the what you call the multi-frame alignment signal. It is used to synchronize the CAS. Bit 5, 7, and 8 are spare bits for use for application, maintenance, or monitoring of performance. Bit 6 is used for alarm monitoring. A is equals to 1 in alarm condition. Power fault, loss of signal, loss of multi-frame alignment. When A equals to 1, CAS bits is equals to 1. Channel associated bits ABCD, channel numbers refer to the telephone channel numbers. 64 kilobits per second channel time slots 1 to 15 and 17 to 31 are assigned to telephone channels numbered from 1 to 30. This bit allocation provides for 500 bits per second signaling channels designated A, B, C, and D for each channel for the telephone and other services. With this arrangement, the signaling distortion of each signaling channel introduced by the PCM transmission systems will not exceed to positive negative 2 ms. When bits B, C, or D are not used, they should have the values of B is equals to 1, C is equals to 0, and D is equals to 1. It is recommended that the combination of 000 of bits A, B, C, and D should not be used for signaling purposes for channels 1 to 15. The next is the limitations. The limitations here is the bit interleaving multiplexing use, which is causes the delay, though it save costs on costly buffers and is, but processing huge data became challenge. Another limitations of PDH or play, Plesiochronous digital hierarchy is the lack of flexibility. Taking out a specific tributaries is costly affair as we do the demultiplex the higher order rates in the reversal order of the multiplexing to get lower order tributaries. As the networks develop, we need a bank of multiplexers, remultiplexing every time we demultiplex. Another limitations here is the lack of consensus on standards. Equipment manufacturers followed different standards and interoperability was an issue. Customers were forced to buy the same equipments as each manufacturers used their own unique designs, decoding or the decoding. No higher standards data interfaces were defined in coherence to the bandwidth demand beyond D55 or the DS5. Only electrical standards but no optical standards through some operators used optical physical layer without standards. Another limitations here is the DOAM was nightmare. Provisions for network management was limited and no established NMS to remotely monitor frequent call drops and QO5 issues. No self-healing mechanism, instead most of the activities were manual. The supervision and maintenance functions are limited. Just a few bits for alarms in FA5 and FAS and MFAS and EBIT or the 2 megabit per second frame used to take from few hours to days to debug the fault and resolve. Defined typically for point-to-point communications and mesh but not self-healing ring support. No room in the signal structures for network management channels. No PRC. Another here limitation is the no PRC. To uniformly manage the whole network individual NEs having their own clock sources which might lead to huge jitter issues. Stuffing in every stage of multiplexing leads to jitter. Main mode of transmission with twisted pair and coaxial cables. To electrical interference or to signal loss, then more repeaters. Another here is of limitation is the family demands more than 100 Mbps bandwidth for voice, data, video streaming, IPTV, and other applications. Then we can think of PDH networks. The standard which overcomes of the above limitations is SDH or sonnets. Next, last is the summary. The summary here is the PHD is a technology for transporting voice or data between multiple devices in which are working with clock sources with accepted tolerance levels for synchronization. Pulse code modulation or PCM is a technique used in PDH networks which is based on the time division multiplexing or TDM. Main mode of transmission was with the twisted pair, coaxial cable, and microwave. Here are the advantages of the PDH. First, here we have equipment small enough for use in street cabinets, good for point-to-point connections, and last is the cost-effective support for access networks. That's all. Thank you.